All right, so once you get past that finite element analysis, so when you go to university, you do things similar to this where we make that assumption that theta is really, really small, and then we can continue on. That's how a lot of formulas are derived. So now that I've kind of convinced you that these two triangles are actually similar, this is where our centripetal acceleration formula stems from. So if they are similar, then we do know that delta V from the second triangle is similar to, in magnitude, V delta T. And we know that the radius, V1, the magnitude of V1, so it would be our V, our velocity, since those V's are going to be the same, corresponds to our radius R. All right. What I'm going to do then, I'm going to do just some simple algebra here. I'm going to multiply both sides by the vector V. All right. So when you do that, we end up with delta V over delta T equals the vector V squared, or your velocity squared, divided by your radius. Now, off to the side here, what is delta V over delta T? So what is change in velocity with compared to time? So your change in velocity relative to time is acceleration. So the theoretical part is what's challenging here, because our formula simply becomes centripetal acceleration. That's what the subscript C is. That formula right there. So this formula is what gets added to your formula sheet. All right, so that's your centripetal acceleration. It's velocity squared over radius. Okay, so there's your centripetal acceleration. So now we can take this information and we can put some different format in. So as we move along, I'm going to give you a couple different versions here. So if we know delta D is equal to velocity times time, the displacement for one cycle is delta D equals 2 pi r. So that's one rotation. All right, so this right here, that's one rotation. So that is the circumference of a circle, 2 pi r. Okay, and that's the time for one. It's the time for one complete cycle, and that means that our delta T. So if delta T, put this in simpler form, is the time for one rotation, then delta T is just our period now. So if you think back to last in the 3U course, we talked about period. It's time for one complete cycle. Same thing here, same thing in grade 11 math. So delta T is equal to capital T, which is your period. So what does that allow us to do now? Well, we can now take our centripetal acceleration formula from the previous page. So centripetal acceleration is equal to V squared over R. And we're going to replace the velocity expression with our new value. So what is velocity? Well, actually, let's back step it one more time for you. Right here. Going back to this formula right here. All right, I'm going to replace delta D with 2 pi r. All right, so I'm just doing a straight substitution here. Okay. V is the velocity. And delta T now, because we're assuming it is one complete rotation, our delta T is now our period. So this is a very specific case. It's when delta T is equal to our period. Isolating for V, we end up with 2 pi r over period. So I'm going to take that conclusion, or that formula, I'm going to plug it in over here to get a new acceleration formula. So 2 pi r over period squared over r. And since we're talking about magnitudes and not direction here, the r's do cancel down. So 2 squared is 4, pi squared, r squared divided by r, we just reduced to r, and that's over the period squared. So there is our next acceleration, centripetal acceleration formula right there. So that one you use if you know the period. Finally, the last version that we're going to have here is that if you know that period is equal to 1 over frequency, then we just do a simple substitution here. So 4 pi squared r over 1 over the frequency f. When you simplify that, you have a fraction in the denominator. It becomes 4 pi squared r f. And there is our third and final equation for centripetal acceleration. All right. So we end up with 3 different versions or 3 different formulas for centripetal acceleration. So centripetal acceleration is equal to, so v squared over r. It's also equal to 4 pi squared r over your period squared, 4 pi r over period squared, and it's also equal to 4 pi r f squared. And the pi's should be squared. Okay, so there are your 3 formulas for centripetal acceleration. Okay, so 3 versions. Now, centripetal force then. How do you calculate centripetal force? Well, centripetal force goes back to Newton's second law, F equals ma. So basically, your 3 formulas will be based on F equals mass times centripetal acceleration. So we're just taking the above formulas and multiplying by mass. So it could be mv squared over r. It could be 4m pi squared r over the period squared. Or it could be 4, doesn't matter the order here, pi squared m r frequency squared. So all 3 of those versions are legitimate versions here. So those are your 3 formulas, or the two sets of 3 formulas that you're going to have on your cheat sheet. So you want to make sure you have all your centripetal acceleration formulas, and you also want to know that you have your centripetal force formulas as well. Okay, and you really only need the acceleration ones, and then put beside it FC equals MAC, and it saves you a little bit of space on your cheat sheet. All right, so all those formulas then allow us to do some of the calculations or some of the word problems that we're going to run into. So I'm going to finish this video up with talking about extending a grade 11 concept that I talked about, and that's something on an inclined plane. So from grade 11, you know that this is your force due to gravity. You know that this is your normal force. You know that this is the force due to gravity down the slope, and then of course you have your force due to friction. So there are 4 basic forces. The new one then that we need to be aware of is the force towards the center of the circle. So this is your centripetal force. Okay, so that is where the direction of the force. Now, I'm going to have people that, and this is going to be where people are going to get somewhat confused, because people know that if you're going around a curved surface, you want to move up the slope, Okay, that's the tendency. You know the object wants to go up the slope. So people are going to be saying, you know, why is centripetal force not up here? Well, the thing that's keeping you in place from actually doing that is this force right here. So we always draw centripetal force towards the center of the circle, even though you feel like it should be going in that direction, pulling you up the slope and flying off the track. All right. So some quick geometry here. Because the bases are the same, maybe change to a highlighter. So what we get is a Z pattern here. That Z pattern tells me that these 2 angles are equal. So that is my theta. So if I want to calculate centripetal force, I also got to find another angle for you here, so that makes sense here. What's the easiest way? So we would know that Right here, that angle is a 90 degrees, which means that this is 90 minus theta. And if we extend gravity all the way up, it's perpendicular in there, so that angle right there would be theta. So that's the angle. We always like to use theta here, and just so you can see where that comes from. But your centripetal force, Fc, is equal to your normal force sine theta. So there is your last formula for the day in order to do these in order to do inclined calculations. So the other ones, again, these ones you should have already, but if you don't remember them, Fgx is your force due to gravity, and that would be cos theta down the slope. Normal force is equal to force due to gravity sine theta. No, I have those backwards. All right, so it'd be over here, the theta. So it would be sine theta down the slope. Cos theta gives you your normal. All right, and you're really going to be setting that centripetal force equal to those previous ones that we already talked about or calculated. So that is the theory. This is definitely, leave it to the end for a reason. I have examples remaining in the third and final video, and then a quick discussion about stuff that's orbiting our planet. All right, so I'll finish this up in a third and final video, and then you can get going on the homework.